Welcome to This Explainer. Okay, today we are going to completely change how you look at one of the most common, seemingly mundane objects in the human world. When you look at a screw, you probably just see a boring piece of hardware, right? Something you grab from a plastic tub to hang a shelf. But by the end of our time together, you're going to see it for what it truly is, a mathematically precise, hidden machine that literally holds modern engineering together. We're going to unlock the physics of screws, pulling directly from our source material on engineering mechanics.
Here's our roadmap. First, we'll unwind the screw, then look at its two main applications, fasteners and drives, and finally, we'll dive right into the physics of friction. Let's get to it.
Part 1. Unwinding the simple screw.
So to really grasp the engineering here, we have to start with a core definition. What actually is a screw thread? Fundamentally, it's a geometrical structure that you can visualize as an inclined plane wrapped around a cylinder. Think of an inclined plane as a wedge or a ramp. That's it. It's one of the classic simple machines, just coiled up into a tiny, space-saving spiral.
Look at it this way. If you take the thread of a standard bolt and mentally unwrap it, you quite literally just get a wedge, a flat, inclined plane. The sheer genius of the screw is that it takes this long ramp, which would normally take up a massive amount of horizontal space to do any useful work, and wraps it infinitely around a central post.
And because of this wrapped-up inclined plane, turning the screw forces the wedge forward through whatever material it's embedded in. It's almost like magic. A helical screw effectively takes rotational motion, you twisting your screwdriver, and instantly converts it into straight, axial displacement. You spin it in a circle and the object moves forward in a straight line. Seamless.
Moving on to Part 2. Fasteners versus drives.
Knowing that a screw is essentially just a wrapped ramp, let's look at how engineers actually apply it. In the engineering hierarchy, screw applications branch off into two very distinct paths. You've got screw joints, which we usually call fasteners, and screw drives. Fasteners are designed strictly to securely hold things together, while drives are engineered to create deliberate, controlled motion.
Let's head down that first path, fasteners, and how they hold things together.
Fasteners act as temporary, non-permanent joints. Now, unlike welding, which permanently fuses metals together, screw joints allow parts to be fitted together and later taken apart. But don't let the word temporary fool you. Take a look at these real-world applications. We've got a motorbike engine cylinder head on one side and a massive bolted flange on a pressure vessel on the other. The sheer scale of responsibility here is wild. They aren't just holding two pieces of wood together. They're securing critical, high-stress components containing thousands of pounds of pressure and intense heat.
Now, here's what is really fascinating about how they maintain that hold. When you apply rotational force, or torque, on a nut, the wrapped inclined plane pulls the bolt tight. This generates an immense contact stress right at the interface of the two parts. It is this intense, highly calculated squeezing force that prevents the engine or the pressure vessel from blowing apart. The screw is actively clamping the structure together under immense tension.
All right, Part 3. Drives. Moving things forward.
Switching gears to the other side of the family tree, screw drives. Here, the goal isn't static holding, it's dynamic movement. And the versatility is absolutely incredible. Engineers use them for gear reduction, like in worm drives. They use them to move crazy heavy objects. Think of a mechanical screw jack effortlessly lifting a whole car. But they are also used for precision measuring, because one full rotation of the screw advances it by a perfectly predictable, tiny distance. Tools like micrometers can translate that rotary motion to measure microscopic dimensions. A lathe machine actually combines both, moving a cutting tool linearly while simultaneously measuring that movement with perfect precision.
Finally, Part 4. The physics of friction.
Okay, time to look under the hood. We need to explore the invisible forces of torque and friction that dictate how all of this actually functions mathematically. For an engineer calculating the forces needed to move a screw, there are two primary scenarios. Case I is when you're rotating the screw against the load, so tightening the screw or using a jack to lift a weight. Case 2 is when you are moving the screw in the exact same direction as the load, meaning you're loosening it or lowering that heavy weight.
Let's start with Case I, rotating against the load. Now, don't let the math intimidate you. The concept is actually pretty elegant. The total torque required, marked as T, depends on the load being moved, which is W. But look inside the parentheses there. We're taking the tangent of the friction angle, which is phi, plus the thread angle, alpha. When you tighten a screw, you're fighting an uphill battle. You have to expend energy to overcome both the slope of the ramp, alpha, and the inherent friction of the materials sliding against each other, phi. That's why we add them together.
Now look at Case 2. Moving with the load. The mouth subtly but crucially shifts. When you're loosening the screw, the load is actually pushing down the ramp, trying to help you out. So inside the parenthesis, we now have phi minus alpha. You are still fighting the friction, sure, but the slope of the thread is now working with the load.
Which leads us to one of the most vital concepts in all of mechanical engineering, self-locking. This only happens when the friction angle, phi, is greater than or equal to the thread angle, alpha. Let's put this into a real-world scenario. When you jack up your car to change a tire, you take your hand off the handle and the jack stays raised. Why doesn't the immense weight of the car just force the screw to spin backwards? Well, it's because the friction angle is steeper than the physical ramp of the thread. The friction literally chokes the motion, locking it in place without any external force needing to hold it.
But, and this is a big but, what happens if you get the math wrong? If the friction angle is strictly less than the thread angle, the screw becomes non-self-locking. We call this overhauling. In this disastrous scenario, there just isn't enough friction to hold the load on that inclined plane. The heavy weight will completely overpower the system, forcing the screw to spin backward and loosen all on its own, meaning your jack would just instantly drop the car to the ground. Yikes.
To make sure that never happens, engineers don't just hope for the best with standard friction, they manipulate the geometry itself. Check out this cross-section of a V-thread, which you'll see on almost all standard hardware. Instead of a flat thread, it's cut into a V-shape. Because of that included angle between the sides of the thread, the normal reaction force, the actual pressure between the sliding surfaces, is increased. By mathematically wedging the thread like this, engineers artificially boost the frictional grip, guaranteeing those self-locking conditions are met even under extreme stress.
So, the next time you see a screw, a bolt on a bridge, or a car jack, you won't just see a boring piece of metal. You're going to see a perfectly calculated inclined plane, relying on the invisible tension of friction and the precise angles of geometry to hold our modern world firmly in place. It really leaves you with a profound question. As you sit there watching this explainer, how many self-locking inclined planes are quietly doing the math, keeping the world around you from falling apart right now? Thank you so much for joining me, and I hope this deeper look completely changed the way you view the machinery of our daily lives.